Hello, here is another video of Math with a Black Rat. Good rat seek. This video is appropriate for second year A-level and assumes fluency with differentiation by chain rule. Integration by substitution is chain rule in reverse. Okay, so I'm assuming that you have fluency in that. Let's recap how chain rule works. Suppose you have a function that looks like this. So y is the sine of 5x squared plus 11. And suppose I'm interested in differentiating that sucker. Well, it's composition. I have composition of functions because I've got this phrase, 5x squared plus 11, stuffed inside a sine function. And we can show that if we do some intermediate variable business. So if I say, let's take the letter u to stand for 5x squared plus 11, then I can write y as the sine of u. Chain rule says, if you want to differentiate something with respect to x, but you've got composition going on, you differentiate with respect to the intermediate variable, and then you differentiate that intermediate variable with respect to x. So here, dy du, that's a very clean thing to say. Dy du is going to be the cosine of u. And du dx is now a much more manageable thing to think about. That's going to give me 10x. Then you say, okay, I don't want to be mix and match variables. I wanted to be in terms of x. U was just an intermediate to help me along the way. So you tidy that up as 10x times the cosine of 5x squared plus 11 and run yourself off the page. Okay. Integration is doing differentiation the other way. So if I'm differentiating the expression sine of 5x squared plus 11, and I come up with 10x times the cosine of 5x squared plus 11. Okay. Sine went to cosine, differentiate the inside, that's how I got the 10x. Then integration says, if I integrate that, I'll come back to what I had originally. So this way is differentiation, but going it the other way is going to be integration. Differentiation and integration, two different directions of the same thing. So if I want to integrate 10x times the cosine of 5x squared add 11 with respect to x. And by the way, this notation is all, I think of it as bookends. This means please perform integration. This means x is the variable you care about. And this is the integrand. In formal language, that's called the integrand. And that's the thing we're integrating. But I know that that thing was the derivative of my sine expression. So if I integrate that, I know because I already did it. It's not that I can magically see it, but here's one I made before. We should come back to the sine of 5x squared plus 11, plus some arbitrary constant. And this is the structure we're interested in. And I want to highlight where all the u's and business went. So we said that u was the expression composed inside the sine function. And here's that u, and here's that u. This piece, that 10x, that was du dx. And it's this kind of structure that we're interested in when we do integration by substitution. We're looking for that du dx business. We're looking for something we can call u. It's very personal. Something we can call u and a du dx involved. Stuck by multiplication because chain rule is about multiplication. Okay, so I want a thing and thing's derivative. And when I observe that, then integration by substitution could be the tool for the job. This is where the bookend notation becomes really important. Integration by substitution allows me to say, hey, you know what? This 10x business was a byproduct of when I differentiated this thing. So it's really this cosine u structure that I've got going on that's going to take me back to the sine of u, because this 10x came out from differentiating, but when I integrate, I kind of pack it back inside. This 10x was a phenomenon of differentiating. So if I'm undoing differentiating by integrating, that 10x is going to get stuffed back inside, and I'm really looking at the structure of cosine of thing. You might want to say that back to yourself a few times. Integration by substitution lets me rewrite this mess as the integral of the cosine of u du. And look, I've changed my bookends. That, ooh, that's a color that will stand out. That is now super duper important for understanding why we care about this bookend piece. Formally, this is called an operator, because it's telling me how to operate the integration. Operate integration by paying attention to u as the variable. No longer x, we're now in u. And it's that u that we did from chain rule. So cosine of u integrates as the sine of u. But then we want it to be an x because that was our original. So we re-substitute. And there we are. We know this one works because here's one I made it ahead of time. Okay. But it's this kind of breakdown structure that we're interested in for chain rule. There's formal ways to write out the notation. I'm happy to show you that. I'm not going to do it in this video because I don't want you to get lost and hung up in abstract notation. I want it to be as concrete as possible. We're already pretty abstract here, but we've got particular examples. Okay, so how do you recognize this business? How do you set all this stuff up? This du dx and this bookend came out and were replaced by a new bookend. This is the key. I'm sorry, the yellow isn't very bright on camera. This du dx business, along with my dx operator, the bookend of my integral, together they get replaced with a new bookend. And I've changed my variable to the letter u because I've replaced that phrase with the letter u. And this is the big structure to remember in chain rule. It's this. You can do a change of variables. In Elizabeth speak, swap out your bookend. I'll say swap for a new bookend. That's a W. By bookend, the formal word is operator. Okay. We change variables in our integral, swap out for a new operator, a new bookend, by the following relationship. The derivative of u with respect to x along with that little dx bookend is going to be equivalent to a du bookend. Okay. Notation, this is your derivative of whatever you decided u is going to represent. Oops, sorry, off camera. This is the derivative of whatever you've decided u is going to represent. This is your operator, your bookend. Okay, and you need that entire conglomeration to swap out for a new bookend, a new operator in your integral. Let's do some examples. Let's do something similar to this, but I'll change the numbers a bit to show you how we set it up. Sorry for the continuity break there. When I change the page, it stops recording. I don't know what's going on with that. Okay, so here's another example. The structures are similar, but I'm going to change the functions a bit. Okay. Suppose we're looking at the integral of 2x e to the x squared dx. And that's a fancy thing to say. It's not a plain old e to the x. It's not a plain old 2x. It's a mix and match of various things. And it's a little bit intimidating, but it's okay because I'm picking nice examples. It's okay because I can apply my substitution technique. And what I'm looking for is I recognize that here I've got composition. It's not e to the x, it's e to the fancy stuff. I have an x squared shoved inside an e to the x. It's important that you're able to recognize this as composition. In addition, that thing stuffed inside the e function, his derivative is right there. You need to have fluency to recognize derivatives. This one is fairly straightforward. 2x is the derivative of x squared. And that's going to set me up. And this is how I do it. I'm going to let u be the thing inside the composition, the fancy thing. And I know that du dx is 2x. And here's my magic bookend swap. Here's my change of variables. That's how you say it formally. You can think of it as the magic bookend swap. I don't know where I come up with these ideas. Where does anything come from? I don't know. Okay, this is your relationship. Du dx, that derivative with your dx operator, your dx bookend, is equivalent to a du bookend. I'm going to use that structure to drop my pieces out. I may have shown you something slightly different in lesson. I'm sorry. It's all the same. It's same of a sameness once you know what you're doing. When you're trying to learn, I appreciate that it can look chop and changey. I promise you it's all the same thing. Here's how you do it. Here's your magic bookend swap. You must learn, you absolutely must learn this like your own name. No big deal. Du dx, the dx bookend, is equivalent to the du bookend. I have du dx, that's 2x. So 2x with my dx piece is equivalent to du. And hey, presto, would you look at that? I have all that mouthful here in my original derivative. I have a 2x and I have that dx bookend. So this is all going to come apart really nicely. Oops, I'm going to write it out to draw all over it to show you. And when you're getting to grips with this technique, it's nice to do this for yourself. So, what colors do I want? Here is my du dx dx, and that's all going to come out for a du. Du du to u and u and u. I have no idea where this comes from. Okay, e is my function, and that's what I called the letter u. So I'm going to rewrite this integral as e to the u, and all that pink stuff swaps out for my new bookend. And presto, this is suddenly a much nicer, tidier, cleaner, easier to integrate affair. This du bookend tells me I'm performing integration by paying attention to the letter u. E to the u, he integrates nicely. That's e to the u plus some constant. Okay, but u is an intermediate. We don't really want to be in the letter u, so I will substitute back with what u stood for. It's so personal. You stood for this, you stood for that. You do this, you do that. So my integration result is e to the x squared plus some constant. And I can check that that makes sense. If you integrate, you get a result. If you differentiate the result, you'll come back to what you were integrating. The derivative of this sucker, you can go through chain rule. E to the thing differentiates as e to the thing, but then you multiply by thing's derivative, there's your 2x. Let's do another example. Let's look at, what do I fancy? What do I fancy? I am fancy and posh. I am not. What do I want to look at? Let's look at, I have a book here to the side. I'm grabbing examples from. Let's look at the integral of 3x squared times x cubed plus 5 to the 1/2 dx. Please integrate that with respect to x. The book originally wrote that as a big ugly square root. So you would have to do the extra step of rewriting it with an index, but let's just take it from here. Okay, that looks gross. There's worse, but this is not particularly pretty to look at. However, I can observe here I've got composition of functions going on. I've got a mouthful stuffed inside a square rooting power function. Thing to the 1/2. And wouldn't you know it, hey, that 3x squared looks an awful lot like the derivative of thing, doesn't it? It's exactly the derivative of thing. So let's call that u. And this business is the derivative of u with respect to x. I keep gesturing with my pen like it makes it more emphatic. This! 3x squared is the derivative of my fancy mouthful inside the composition. And that's going to be lovely. So here's how we write it out. U is going to be x cubed plus 5. Never do things in your head, always write it out. The derivative with respect to x is 3x squared. And here's my magic swap. And honestly, I encourage you to write out the magic swap. Some teachers will do other shortcuts, show you other quick ways to get to where you need to be, or maybe they'll think that's the formal proper way to do it. And I worry that some teachers haven't seen chain rule and substitution laid out in formal terms, and so they don't know to teach it more fat and fully, and I awake at 3 a.m. sometimes over it. It's already 2 a.m. as I'm recording this. Okay, this is your magic bookend swap. Your change of variables. We're changing operators. So we're swapping out the dx operator for the du operator. I don't want to integrate with respect to x. I want to integrate with respect to u. But I can't just rub it out. I have to take that derivative piece with me. So this is what I mean. So we've got our hands on du dx from what we decided. So that's 3x squared dx is going to be equivalent to du. Sorry, that was the sharp edge of my pencil. 3x squared with my dx operator is going to be my du operator, and I've got the whole thing right there. So this is an easy swap everything out. So du dx, that's swapped out for du, and I've got u to the 1/2 du. I've got u to the 1/2, right where I want you. Right where I want you. It's beyond midnight. I can't account for myself. I can't account for the math. So this is a power function. We know what to do with power functions. We add 1 to the power, divide by the new power. Arbitrary constant. Dividing by 3/2 is the same as multiplying by 2/3. I thoroughly encourage you to be fluent in that. I'm not going to talk it through any further here. If you feel unsettled, hit me up. U is the intermediate. We want to be back in x. So finish it off as 2/3 x cubed plus 5, quantity to the 3/2 plus c. We're done. There's our result. Pretty slick. Slick. I think this is slick. It's nice. It's a really nice technique. Okay. I'm going to do the same thing again, but I'm going to take the 3 away. And I'm going to show you why everything is still all right. Please don't stop camera. Please keep recording. Yay. Right. Here we are. Same affair, but without the 3. X squared, brackets. X cubed add 5, quantity to the 1/2 with respect to x. That's a funky x. What do your x's look like? There we go. Okay, this is going to be the same kind of affair. I observe that I've got composition of functions. I've got a phrase stuffed inside a power function. And the derivative of that guy, I know it's 3x squared. I don't have the 3, but I do have the x squared. Don't worry about a missing constant. Well, worry, but you can still do the technique. Don't worry about a missing constant. In this case, the 3. Okay, we can cope. If you're missing x bits, we're in trouble. We have to rethink or do substitution by a more subtle way. But if it's just a matter of a multiple, you're going to be okay. Here's how it works. Ah, my colors. Okay. That's u. This is almost du dx. It's going to be okay. Here we go. U, x cubed plus 5. Du dx, 3x squared. Okay, here's our magic equivalence. Du dx dx is equivalent to du. This is our magic box. We love this magic box. You must learn to love it because I say so. So here's our du dx, 3x squared dx is equivalent to du. And you go back to your original and you're like, I don't have the 3. I have the x squared and I have the dx, but I haven't got the 3. Okay, you know what? We can divide by a constant. Let's just divide by a constant. So here's my swap. And notice I am not dividing du by 3, I'm multiplying it by a 1/3 because I need that du to function as a bookend. It's not a piece that moves and interacts with other pieces. It's the bookend that tells me how to do the integration. So I want that 1/3 to be a movable part. And here's how you swap it out. X squared dx swaps out for 1/3 du. That's u to the 1/2. Okay, this, what color did I use? This 1/3 du is my x squared dx. And that 1/3 makes up for the missing 3. Some books, some teachers teach a different way to come to that 1/3. They're not wrong. There's multiple styles. I think this is the most straightforward way to think about it. I think this is the most straightforward way without having to create something from nothing. Some teachers say, well, you can create the 3 up here if you divide by a 3 because it's just the number 1. And that's true, and we do magic tricks with the number 1 sometimes. I've done magic tricks with the number 1 like that sometimes. But I think this is more methodic. I think this is less taxing on shoehorning something into what you need it to be, because you can just follow this method and it will take you where you need to go. I like it too. I just heard you say that you like it. I'm going to pretend that I heard you say that you like it. Okay, this is a power function. This is very deal withable. So I've got my 1/3, I take my u, I add 1 to the power, divide by the new power, arbitrary constant. Now I tidy myself up. That's going to be 2/9, and I'll come back into x world. That was my u. And there I am. There's my result. And you can check this. If you take your result from integrating and differentiate it, you should come back to your integrand. It's slightly off camera, sorry. If you differentiate your result from integrating, you should come back to your integrand. And you will. The 3/2 comes down, interacts with the 2/9, knocks a 1 off of it, times the derivative of the inside, and that 3 is going to interact with the 1/3 that's left, and you're going to come back to here. Let's do some more. Yay, this is fun. This is better than sleep. It is now 2:34 in the morning. For me. I hope you're not up at stupid o'clock watching math videos. Okay, so, what's another nice example to do? Let's look at, looking in my book, let's do a trig one. Let's do the integral of sorry, I'm just looking in my book for, they're all fun and beautiful things. Let's do this. The integral of the cosine of x times sine cubed x dx. Okay, and you might be like, what? And you might be thinking about all fancy trig substitutions you can do, and sometimes we need to do that. I mean, once life starts getting interesting, you have to think about what you're looking at and what tools might apply to the job at hand. That's experience and exposure and learning skills. We are in the context of substitution, so this is going to be a substitution kind of affair. So I'm looking for some composition. I'm looking for thing and things derivative. Let's write that down. You should put that in your notes. You're looking for composition, and you're looking for thing and things derivative. Really formal math. Thing and things derivative. Okay. I've got composition. I've got sine x stuffed inside a cubed function. And if that notation makes you feel itchy, it's perfectly fine to do that. And now it's more obvious that I've got composition. Through sheer force of decades of exposure, this is natural to me. But you can always write it like this, and that's really useful when you're trying to get to grips with fancier things. Take some pressure off your brain, write it like that. Then you can think about the substitution rather than the notation. It's always fine to do that. Gods know why we do that. Okay, sine x is shoved inside a cubed function. And hey, wouldn't you know it? Cosine is the derivative of sine. So I have got thing. This is thing. And this is thing's derivative. We say that more formally with u and du dx. Let's write it out. Okay, let u be the sine of x, and I will be, no, let u be the sine of x, du dx is the cosine of x. Imagine if I did all my lessons at 2 in the morning. Think of the conversations you'd have with me. As if the ones you have already during the day aren't surreal enough. Okay, u is sine x, du dx is cosine x. Here's my magic box. Du dx, dx, say it with me. Du dx, dx is equivalent to du. This is your magic operator swap box. Swap box, what the hell? Okay, it's this structure that's going to save you every time. Save me, save me. Du dx, that's cosine x. Dx is my bookend, and that's going to be the same as the du bookend. So that's going to come out for du. I'm going to have u cubed. I've run myself off the page here. I've got the integral of u cubed du. That just comes off camera. Hey, straightforward power function. 1/4 u to the 4th plus some constant, swap back in for x. 1/4 u is sine x to the power of 4 plus c. It is fine to leave your answer like that with brackets to the 4th. If you want to say sine the little 4x, that's cool. Just like we did sine cubed, you can do sine 4th. If you want to leave it like that, hey, by all means, leave it like that. And that's your answer. That's the integral of that thing. And maybe you're starting to feel the swing of it. Let's do some more. Please don't stop, Mr. Camera. I know, it's so exciting. He's such a good rat. Well, he's mostly a good rat. You should see all the things on the floor he's chewed up. Okay, here's do another one. Here's another one to do. Let's do another one where we have to fiddle the constant, because that's good fun. Let's look at x squared and x cubed are so heavily used. It's hard to think up other things. Heck. All right, let's do x to the 4th times 8x to the 5th plus 19 all to the, what number do you like? 7, grand. All to the 7th. Boy, that's a mouthful. That's fancier than what I'm seeing in my book. But it's just numbers, right? It's just numbers. How hard can it be? I need that on a t-shirt. It's just numbers. How hard can it be? All right, what the hell am I looking for? I am looking for composition. Have I got composition? Yeah, I've got composition. I've got that mouthful stuffed inside thing to the 7th. I've got composition right here. And wouldn't you know it, that thing, his derivative, chin scratcher. I drew on myself. It looks like, it's not Zeke's bite marks. This is purple ink. Zeke doesn't bite much. This derivative is going to be 40x to the power of 4. I do not have a 40, but I do have an x to the 4, and we're not going to worry about the constant. So here's our affair. So here's u, our thing. Here's almost du dx. We can cope with the constant. Here's the formality. Let u be 8x to the 5 plus 19. Du dx is 40x to the 4. Here's our magic box. Du dx, dx is equivalent to du. I hope the sound is picking up okay on this. I'm really sorry if I'm quiet. I'm not shouty because my neighbors are presumably asleep. Who knows? My neighbors might be awake doing math next door, and we never know because we never talk to each other. I'll assume that they are. I'll assume that they're up and doing math. Everybody's awake and doing math. Okay, here's your magic box, right? That's your bookend swap, your operators, your change of variable, but I need that derivative piece. And I do. I have a 40x to the fourth. My dx bookend is equivalent to my du bookend, but I'm missing that 40. No worries, divide both sides by 40. X to the fourth dx, or rather, 1/40th of both sides. Please, 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 please do not do this. Please don't do that. It's bad grammar. I have seen WJEC do all sorts of terrible typesetting with the operator in an integral. And it makes me want to grab somebody and slap them in public and say, do not ever do that again. I will be, when you see a headline that says, exam official slapped around by local woman, you'll know it's me. Okay, so this is where we need to be. I have an x to the fourth. I have a dx. That's all going to come out, not just for a du, but I'm going to have to throw in a 1/40th as well, along with that du. No problem. Here we go. Have you ever been to New York? I went to New York 2 years ago, and they were all, no problem, no problem. It was wonderful. Loved it. Could not get enough. Okay, x to the fourth dx. That's going to throw in a 1/40 and a du bookend. I'm guessing how much space. Sometimes you have to rub out and do it again. There's my u to the seventh. Too much space. Fine, too much space. There you go. Hey, power function. No problemo. I have my 1/40th. Thing to the new power, divide by the new power. Arbitrary constant. What's 8 times 4? Is that 32? 320. Swap back for x. Plus c. That was wild coincidence about that 8 and that 8. That's just happy accident. My subconscious. Okay, so this isn't so bad. This is your saving grace. You're looking for composition and thing with things derivative. If you're off by a constant, not a big deal. Okay, I promised you some integration by recognition and how it's actually chain rule all along. And I'm going to show you that now, and you can decide what you want to do with yourself. Okay, so I hope everything's okay so far for you. I know this is a bit of a long video. Excuse me. Okay, so when you've got something linear that you want to be your u, my goodness. Perhaps something like e to the, it's another number. What number haven't we used? What number haven't we used? 6? Okay. E to the 6 dx. This is composition. And I can do this. I can say u is 6x, du dx is 6. Here's my magic box. Du dx is equivalent to du. Your goal is to have some speed. It's going to take lots of practice to build up your speed, but you need to be relatively swift about it because you don't have time in an exam to faff. Okay, so I see the thing. That's my u. Du dx is 6. Here's my magic box. 6 dx is equivalent to du. I don't have a 6 to mop up along with the dx. That's okay. Constants are not a problem. I'll mop up that dx with a 1/6 du. So my integral becomes 1/6 e to the u du. All along with this, pause the video and look at it again if you're uncertain. I really hope that you're writing this along with me. I should have said that at the beginning. Go back to the beginning of this video and write out the examples along with me. You work it along. You see how you get from step to step. I already know how to do this, This is for you, and so you know how to do this. Okay, I am moving a little bit swiftly. When you're as fluent as I, you'll do it as swiftly too. You're learning. So here we are, 1/6 e to the u du, no problemo, 1/6 e to the u because e is a nice function plus some constant. Come back into the world of x's, e to the 6x plus c. Bob's your uncle. And if this is what you do every time, that's absolutely fine. You can go through the theory again if you're, you're swift, you're not taking minutes and minutes and minutes to do it. This will get you home every time. A-okay, no problemo. Trips to New York for everybody. You will find through force of exposure, and sometimes teachers and books teach it directly, because that was a 6x and not anything fancier, it was just a linear function of x, it's going to throw out that 1/6. And sometimes this is taught as its own subject before you get into formal substitution. As a tutor, I feel really 6 of one, half a dozen of the other about it. It depends how my students' brains work. It depends, what path do you take through the park? It depends on your mood, how your shoes are, how much time you have, who you're walking with, but it all takes you to the same place. So here's another one, similar style. If I'm integrating the cosine of 17x, why not? 17. Okay. Well, I know cosine integrates as minus sine, but I'm going to divide by that 17. So I'm going to have minus 1 over 17. Sorry, I co-opted my negative sign. A minus 1 over 17 sine of 17x. And that came because of that. And if that is comfortable, great, carry on. If this bothers you, here's the story. Treat it as a substitution. I've got composition. Okay. His derivative is just a plain old 17. Nothing fancier than a constant 17. No variables, no nothing else, just a constant. I haven't got that constant, but we know it's not a problem. So if going from here straight to here just wigs you out and your brain won't do it, and that's fine. Some people's brains don't. It's not a problem. It's why we have notation. It's why we have methods in math. It's why math isn't taught. Math should never be taught as, hey, just look at it. Don't you see it? Pants to that. Stronger words than pants. Heck to that. Math is about pattern recognition and then notation to support you through the pattern. If you could just figure out story problems by thinking about it and scratching your chin, we wouldn't have frickin' algebra, would we? Damn it. All right, so if your brain doesn't do this, here's the method. U is 17x. Du dx is just a plain old 17. Here's your magic box. Du dx is equivalent to du. So 17 dx is equivalent to du. Sorry, I'm running off the bottom of the paper here. But I don't have a 17. I have a dx, but I don't have that 17. No problemo. 1/17 du. And now we're integrating 1/17 cosine 17x dx. Sorry, I'll go into the next page. Okay, so, oh, wow. No, that's not quite right. Excuse me, I'm going way too fast. It's almost 3 in the morning now. Let's do this again. Beg pardon. Cosine 17x. You're already at this solution. Good. Okay, so the integral of cosine 17x dx. Okay, u is your 17x, du dx is 17. Here's your magic box. Du dx dx is equivalent to du. 17 with my dx operator is my du operator. I don't have the 17. So dx is equivalent to 1/17 du. Now I can swap my pieces out. Dx swaps out for 1/17 du. Cosine 17x swaps out for a cosine u. And here's my 1/17. You can keep your constant inside the integral or outside the integral. That's personal choice. Sometimes I put it outside so I can think about the function and just keep that as a multiplier. So 1/17, cosine integrates as minus sine plus some constant. So there's my minus 1/17. Sine, swap back in. There you go. So if your brain just doesn't see how that 17 throws out a 1/17, you might over time become comfortable with that. You might want to spend some time thinking through it, develop the skill. That's great. But if you don't like it, you've always got substitution. Always, always. I think I'm going to do one more. Let me think about what I want to do. I mean, there's billions of examples to go through. So, and again, they are all same of a sameness. It's the same technique, but when you start getting fancy about stuff, it's difficult to spot how it's the same, or there's some little variation to it that if you haven't seen it before, it can be a real head scratcher. So if you are going through any of this stuff and you're just like, what? Drop me a note. Drop me a note. We'll talk it through. It's okay. I don't mean any of this to be a, so there, now it's obvious to you and you can do everything. No. No, I hate the word obvious. Obvious is not a useful word. Like I said at the beginning, I'm trying to show you the starting ground for this technique. You have to be comfortable with the starting ground of it before any of the fancier applications are gonna work for you. God, that really looks like I've been bitten, doesn't it? The fancier stuff is absolutely deal withable, but you need a solid grounding in this, in these sorts of examples. Okay, one last one, then we'll call it a wrap. Let's do, really should do a natural log one, shouldn't we? I have lots to say about natural logs. Unnatural logs. No. Just natural logs. Heck pants, stuff and things. All right, let's do this. Let's do 1 over, we'll pick on x squared again, and we'll do, did you say 5? 5x cubed plus 14 dx. The numbers, I mean, I can make up higher powers, but why? We're looking at the structure. Okay, so what was I banging on about? You're looking for composition, and you're looking for thing and things derivative. So I give you that, and you're like, Elizabeth, that's a goddamn fraction. Pardon my French. That's a fraction. Okay, it's a goddamn fraction. I don't see composition here. What the hell are you talking about? Here's a composition. You've got a 1 over x going on. How do I know that? Experience. Somebody told me. I was shown it as a student. I saw things like this. I saw worked examples. I got the hang of it from there. I didn't magic this up by myself, thinking it through. Maybe. Plenty of free time. Maybe you can derive it for yourself. Nobody's expecting you to derive this stuff for yourself. You do it by seeing examples and having conversations. Okay, this is composition with 1 over x. So instead of 1 over x, I've got 1 over 5x cubed plus 14. And that's what I'm recognizing here. I've got a 5x cubed plus 14 in place of an x in the function 1 over x. So I've got 1 over thing. So thing is composed inside the 1 over x. Is that making sense to you? It's 2:56 in the morning. I can't tell what makes sense anymore. If this composition does not make sense to you, drop me a note. I'll say more. I'm going to assume right now that you're okay with this. We're going to go on with the integral. So not only do I realize that I've got thing composed in a 1 over x format, but wouldn't you know it, that's thing's derivative. Here we go. And it's frequently the case at A level that when they give you goddamn fractions, pardon, the thing on the bottom tends to be, not always, but it tends to be u. And the thing on the top tends to be thing's derivative. So that's something to be looking for. Okay, so my u is going to be 5x cubed plus 14. Du dx, you're ahead of me, 15x squared. Well done. Oh, we don't have the 15. Not a problem. We've got the x squared. We can cope with that 15. No problem. You have to go to New York. I loved it. I just loved New York. What city do you love? Do you have a city you love, or a place, or a national park or something? Okay, so du dx 15x squared. Just shut up and do the math, Elizabeth. Right? Okay, so x squared dx is 1/15 du. Grand. I've got that. My original. I'm going to swap all that out for 1/15 du, and that's going to be 1 over u. So my integral is 1/15 1 over u du. Well, hey, style choice, pull the 15th out, and 1 over u, that's your natural log affair. I'm assuming you're comfortable with that. Your unnatural log affair. Okay. 1 over thing is natural log of thing. And hey, we're almost home. Slap it back into x, 1/15 natural log, what was, here's our substitution, 5x cubed plus 14 plus c, there you go. Okay, I hope this is helpful. Please yell. There's oceans more examples. I'm happy to send practice if you don't have enough. If you look at past paper questions, they start to get a little fancier because they are, okay, everybody understands the technique. Do you see what to do with this thing? That's what exam questions are. So if you're trying to learn the technique, it's sometimes a rough place to work. But you do ultimately need that level of fluency. So be sure to look at some of the fancier exam ones. They will all be doable. They will all be approachable. They will all be, oh yeah, it's same of a sameness, but you won't see the sameness until you're fluent with this stuff. Shut up, Elizabeth. It is now, ooh, it's only 2:59. I'm going to make you sit with me and watch the clock until it changes to 3. Okay, that's the video. I hope it's helpful. Yell with any issues, problems, comments, and thank you for watching. Take care of yourself. Zeke is hoping you have a Freddo. Do you have any Freddos? He may have eaten all the Freddos.